let's review the four biological biases that we introduced briefly last time. The first of these is adaptationism. We talked about that a little bit in class, and the example we used was our pinky finger or your pinky toe. Let's consider perhaps a better example, and that would be the panda, in particular the panda's thumb. Pandas are carnivores. They're in the mammalian order Carnivora, so they're affiliated with tigers and lions and wolves and canids and things of that sort. And as a result, they historically, evolutionarily at least, were meat eaters, just like grizzly bears and polar bears and black bears. But the panda bear exists exclusively on a diet of bamboo, and that presents all sorts of problems. Their intestinal system is designed for meat, not plant material, so they have a problem. They have an adaptation to that, though, and that is a thumb. And what the thumb does is it enables them to strip leaves off bamboo so that they're able to consume bamboo more efficiently. Bamboo is not a high-quality diet, does not have a lot of nutritional value, and as a result, anything that they can do in order to improve their efficiency is going to be selected for. But when you look at the panda, when you look at the panda's thumb, what you realize is, if I can get this to advance, there we go. What you realize is that, like any other mammal, any other vertebrate really, they have only 5 digits, not 6. And you can see them right here. You can count them. There's 1, 2, 3, 4, and there's the 5th one, or you can count the claws, 1, 2, 3, 4, 5. So they have 5 digits just like any other animal. But then when you look carefully, you see this other structure right here, and there is the thumb. Okay. Now, it's not like a thumb that you might have that you can bend. This thing isn't mobile, and it's actually not a digit at all. It's simply an extension of the radial sesamoid bone. So it's not really a thumb. If this were a true perfect adaptation, it would be structured fundamentally differently. You would be able to bend it and manipulate it and things of that sort. It's not like that at all. It's not perfect. It's simply a device which is developed from the radial sesamoid bone, which improves efficiency a little bit, but it's certainly not an adaptation. Or I'm sorry, it's certainly not a perfect adaptation. The next bias that we want to consider is this idea of progressivism. This is sort of the biological ladder of life. And the way it's typically illustrated is something like this. So at the bottom you have lower plants and then higher plants and then jellyfish and insects and then fish, reptiles, birds, mammals, and then the pinnacle of all mammals would obviously be humans. And you've probably seen this expressed in a diagram that looks something like this, where you have some sort of low-level primate, right? Actually, it is a great ape, right? But followed by something that's slightly more advanced, and then Neanderthal man, and then Neolithic man or something, and then humans right here. And of course, if we were to continue this, there would be businessman at the far end. This is sort of a silly idea, right? This idea that evolution progresses or has progress. That's not the way it works at all. We are not changing towards anything. We are simply humans. And all organisms on the planet are either successful or they're not. If they're extant, they're successful. If they're extinct, they were unsuccessful. All species go extinct. The average lifespan of a mammalian species in the fossil record is about 7 million years, 6 million years, something like that. So humans are a good middle-aged species. So far within the fossil record, every species that has ever existed has gone extinct, and there's no reason to think that we will be any different. Organisms don't progress towards anything. They simply are what they are. They're either successful or they're not successful. The next idea that I want to consider is this notion that that evolution is gradual, and that's not true either all the time. Here on the right side of the image you see two comparisons. One is the gradualism model and the other one is punctuated equilibrium. In the gradualism model, species accumulate mutations over time, and this is usually a slow process, so that they very slowly develop into something that is different from where they started. In the punctuated model, what happens is that when the species splits off, initially you have some rapid evolutionary change, and then you get this long period of stasis. So over here on the far right side, there's this period of phylogenetic change, and then from here all the way up to here, the species is the same. There's no longer any evolutionary change. You can get another perspective on this by looking at the history of life here, and we can see a number of mass extinction events. So this is time on the x-axis, and then number of species on the y-axis. And this is just for marine organisms, so it doesn't represent exactly what's going on for terrestrial organisms. But you can see that there are a number of extinction events. Here, for example, the first one right here is at the end of the Ordovician. There's another one here at the end of the Devonian, one here at the end of the Permian, right? And this end Permian mass extinction event is pretty significant. And that's the one which makes it possible for the reptiles to evolve. And this, of course, is the period when the reptiles ruled the Earth. And then notice here there's another mass extinction event at the end of the age of reptiles, and then that leads to another adaptive radiation. So what happens in this model, for example, here in this period, you have this long period of stasis, right? So there's a mass extinction event, there's an adaptive radiation, and there's a long period where the number of species basically stays the same, and there's not a lot of change in the species that are there. That happens again right here, right? And that's what's happened in our own era as well. And of course, you understand that we're in the midst of yet another mass extinction event. So this whole notion that evolutionary change is always slow and gradual is sort of silly. It's clear that there are periods of rapid evolutionary change, right? That's illustrated here when you have these very rapid adaptive radiations. Those things show up again and again and again and again, right? And then you have long periods of stasis where there isn't much happening. The final bias that I want to talk about is determinism, and this is essentially a racist kind of an idea, and it comes from this notion. It actually has its origins in craniotomy and things of that sort, where there was this basic idea that the races could be discriminated against or discriminated between on the basis of brain size and brain volume. And the idea was clearly that white people have the biggest brains, and black people have smaller brains, and Indians and Asians have smaller brains as well. So there was this entire period of scientific study in which that was simply accepted to be true. I mean, there was no question in that at that time that white people were superior, and that's why you have this sort of notion of the Greeks, having this supreme intelligence and these big heads, and then of course the other races, the Asians and the Africans, would have smaller heads and less intellect. And here you can see this in this list of sort of attributes that would be associated with the lower races. Things like long arms, insensitivity to pain, scanty beards or baldness, shifty eyes, hawk-like noses and fleshy lips, big chins and prominent appearance, big ears, flattened or upturned nose, high cheekbones, large jaw, forward projection of the jaws, things of that sort. The sorts of things that you might associate with some of the great apes. But it clearly has a racial underpinning. And of course, one of the whole ideas behind this was an effort to justify the slavery, right? The moral authority to keep and own slaves, which is, I think, clearly no longer a viable argument. At any rate, the basic biological idea was that organisms had a certain biological inheritance, right? And that's what they were stuck with. You'll recall from our discussion we talked about the idea that your phenotypic expression is partially a consequence of your genotype, but it's also a consequence of environmental influence and interaction influences. And what that means then is that this whole notion that you are determined by your genetic heritage is not correct, right? There are many people that have done incredible things, and if you were to look simply at the genetics, you wouldn't think that that would be true. But the environmental component and that interaction component of your phenotype turns out to be very important. All right, that's it for today. See you on Monday.